Okay, this is section 2.6, video 2. We're going to go ahead and finish up section 2.6 with this video. So we were talking about implicit differentiation, taking a derivative of something with respect to x, meaning that if you have y's in your function and you take the derivative, you have to tack on a dy dx. So let's go ahead and do a few more examples. So the first one here, number 3, 2 sine of x cosine of y equals 1. First thing I'm going to do is I'm going to say, okay, I want to divide both sides by 2 to kind of get that out of the way. So we're going to have sine of x cosine of y equals 1/2. The nice thing about doing that is when I take the derivative of the right side of the equation, it's going to be 0. Now we do have to deal with the product rule on the left side. So we're going to have a product of sine x cosine y. So the derivative is going to be the derivative of the first, which is cosine x, times the second one, cosine y, plus the derivative of cosine y. The derivative of cosine, of course, is negative sine of y. And then the chain rule applies. Now the derivative of the angle y, which is dy over dx. And then times the first term, sine of x, equals the derivative of the right side, which is 0. Now we need to solve this for dy over dx. So we'll keep the dy over dx on the left-hand side. So we're going to have negative sine of x, sine of y, dy over dx equals negative cosine x, cosine y, and that's subtracting the cosine x, cosine y to the right. Now we can solve for dy dx, dividing both sides by negative sine x, negative sine x sine y. So we'll have negative cosine x cosine y over negative sine x sine y. So the negatives cancel out, and that gives us a positive. I've got a cosine x divided by sine x, which is the same thing as cotangent x, and I've got cosine y divided by sine y, which is cotangent y. And that's it. That's the most simplified form of our derivative. Okay, number 5. Evaluate f prime at the point 2, 3 when f of x is 9x squared minus 3x. Okay, so you might look at that and say, wait a minute, that doesn't look the same as what we were just doing. You're right, it doesn't. We don't have any extra y's in this thing. So when I take the derivative, it's pretty straightforward. F prime of x, we can just use the power rule. 18x minus 3. But it says to evaluate it at the point 2, 3. Well, at the point 2, 3, there's only an x value that I have to worry about. So really, I'm just evaluating this at 2, which is going to be 18 times 2 is 36 minus 3. So we're going to get 33. And that's the derivative evaluated at the point 2, 3. Now, why did I show you that one? Because that's like what we've been doing. Let's do the next one. Okay, so we want to find f prime at the point negative 1, 1 when x plus y cubed equals x cubed plus y cubed. So we have to take the derivative of both sides of this equation. I've got y's in both sides, so it's definitely going to be something where I'm going to have to use implicit differentiation. All right, so the derivative of the left side, it's a chain rule to start with. So it'll be 3x plus y squared times the derivative of the inside. I've got x plus y on the inside. So the derivative of x is 1. The derivative of y is dy over dx. And then the derivative of the right side is going to be 3x squared plus 3y squared dy over dx, because remember, you have to do the y part implicitly. Okay, it says we're supposed to evaluate f prime when x is negative 1 and y is 1 at that point. You could solve this for dy over dx. A little bit more trouble to do algebraically, or we just took the derivative, so now I'm allowed to plug in the values. So I'm going to plug in negative 1 for x and 1 for y. Fortunately, it's going to work out really nicely in our favor here. So I'm going to have 3 times negative 1 plus 1 squared. That part's going to be really nice. plus 1 over dy over dx equals 3 times negative 1 squared plus 3 times positive 1 squared dy over dx. And why did I say that the part on the left was going to be nice? Well, if you look in the parentheses, negative 1 plus 1 is 0. Square that, it's still 0. Multiply it by 3, it's still 0. Multiply it by 1 plus dy dx. Guess what? It's still 0. So the whole left side is still 0. On the right side, now you just got to be careful. Square the negative 1 and you get 1. So you're going to get 3 out of the first part. And then you're going to get 3 times dy over dx out of the second part. This is much easier to solve now. Simply subtract 3 on both sides, and then divide both sides by positive 3, and we get that dy dx is negative 1. And that's what dy over dx is at the point negative 1, 1. It's going to be something completely different at a different point on that expression. Okay. Number 5, find the slope of the circle x squared plus y squared equals 25 at the point 3, negative 4. So let's go ahead and take the derivative implicitly. So the derivative of x squared is 2x. Derivative of y squared is 2y dy over dx equals the derivative of 25, which is 0. Solve for dy dx. Well, you don't really have to. We can plug 3 and negative 4 in right now, as a matter of fact. So let's do that. So we're going to get 2 times 3 plus 2 times negative 4 dy over dx equals 0. So we get 6 minus 8 dy over dx equals 0. Subtract 6 on both sides, and then divide both sides by negative 8. Negative 6 divided by negative 8 is going to reduce to positive 3/4. Now, we didn't have to go through all of that. If you remember from the first video, that the derivative of a circle, and this is the nice thing, the derivative of a circle is always going to be the same thing as long as the circle is centered at the origin. The derivative was negative x over y. If you remembered that, then all you have to do is plug in the x and plug in the y, and you're going to get exactly the same thing. Just a little shortcut if you happen to remember that the equation of a circle's derivative is always going to be negative x over y. If you don't, no big deal. It's not that hard to take the derivative. Okay, in number 8, show that the slope dy dx is defined at every point on the given graph of 2y equals x squared plus sine y. Well, in order for me to show that the derivative is defined everywhere, I guess I should probably find the derivative first. So let's take the derivative. Derivative of the left side is going to be the derivative of 2y, which is implicit. So it's 2 and then times dy over dx. The derivative of the right side, derivative of x squared is 2x. The derivative of sine of y is cosine y times dy over dx. Okay, so now we need to solve this thing for dy over dx. So I'm going to subtract the cosine y dy over dx to the left. To me, that's just the way that made the most sense. Equals 2x on the right. Factor out the dy dx. And then divide both sides by what's in the parentheses. So we get that our dy over dx, our derivative, is 2x divided by 2 minus cosine of y. Well, it says we want to show that the slope, which we just found, is defined at every point on the graph. Well, for it to be defined everywhere, that means there can't be any kind of 0 in the denominator. So basically, for this to be defined everywhere, 2 minus cosine of y cannot equal 0. Well, if it does equal 0, if I add cosine of y to both sides, is there any angle that I can plug in for y that cosine is going to equal 2? No, there isn't. This is never going to be the case because cosine is only going to bounce back and forth between negative 1 and 1. Cosine will never give you a value 2. So since that's the case and cosine can't equal 2, Therefore, those three dots, by the way, that's a shorthand notation for therefore, dy over dx is defined everywhere. Obviously, there's nothing in the numerator 2x that could have given us a problem in that case. Okay, we're getting there. Okay. Definition, something that you may or may not know. The normal line, something not the tangent line, the normal line is perpendicular to the tangent line. So a normal line is perpendicular to a tangent line. So we want to find the tangent line and the normal line to the ellipse, which is given as x squared minus xy plus y squared equals 7 at the point -1, 2. Okay, so this is the general idea. We've got some kind of an ellipse, which is just basically a kind of a stretched out circle. And we want to find the equation of the tangent line and the normal line at -1, 2. So I'm just going to kind of assume that maybe that's like, I don't know, right here, -1, +2 maybe. We want to find the equation of the tangent line, which is going to look something like this. And we want to find the equation of the normal line, which is perpendicular to that, which is going to look something like this. So the orange one is normal, the green one is tangent. In order to find either one, we need the slope. All right, so let's go ahead and at least take the derivative. So we're going to take the derivative. That's going to be 2x minus, got a product rule here of xy. Derivative of the first one is 1 times the second one, plus derivative of the second one, which is dy over dx, times the first, x. That's the product rule. Plus, derivative of y squared is going to be 2y dy over dx equals the derivative of 7, which is 0. Okay, again, I need to find the derivative at the point -1, 2. So let's go ahead and plug in -1 and 2 for my x's and y's. So we're going to get 2 times -1 minus 1 times 2 is 2, plus, let's see, we're going to get -1 dy over dx, plus 2 times 2 is 4 dy over dx equals 0. So this is going to be -2. I'm going to distribute the minus, so we're going to get -2 plus dy over dx plus 4 dy over dx equals 0. Combining like terms, I'm going to get -4. I've got 1 dy dx plus 4 more dy dx's, so really I have 5 of them. And then to solve this for dy over dx, I'm going to add 4 to both sides. And then divide both sides by 5. So we get that our slope is 4/5. So the question is, what am I going to do with that? I mean, I know I can write the equation, I know I can write the equation of a tangent line given that slope, but how's that going to help me with the normal? Well, this right here is the slope of the tangent line. For something to be perpendicular, the slopes are opposite reciprocals of each other. So the slope of the normal line is going to be the opposite reciprocal of 4/5, which is -5/4. So now I have everything that I need because I've got my x and y right there, and I've got my slopes. So the equation of the tangent line is going to be y minus 2 equals 4/5 x minus -1 or plus 1. The nice thing is, everything here is the same for the normal line except for the slope. It's still y minus 2 equals, now the slope is going to be -5/4 x plus 1. So this one right here is the tangent, and this one is the normal. And that's it. All right, one more page to go. So implicit differentiation can also be used to find derivatives of higher order. So we could find a second derivative or even a third derivative, which would get really messy, but we'll just stick with the second derivative in this case. So the idea is it's pretty much the same as the idea for a first derivative. You have to do the first derivative implicitly, and then you're going to take the derivative of that to do the second derivative. So we want to find the second derivative of x squared y squared equals 10. All right, so it's definitely a product rule. We're going to have to find the first derivative first. So let's see, the derivative of the first term is 2x times the second term, y squared, plus derivative of the second term, 2y dy over dx times the first term, x squared, equals the derivative of 10, which is 0. Okay, now in this case, we definitely have to solve this for dy over dx. We're not plugging anything in, so let's solve it. So I'm going to subtract the 2xy squared to the right, and that's going to leave us with a 2x squared y dy over dx equals negative 2xy squared. Divide both sides by 2x squared y. You get negative 2xy squared divided by 2x squared y. And technically that's your derivative. Now I'm going to want to definitely simplify this one. So it looks like the 2's here are going to divide out. I'm going to have one of these x's divide out with that one, and I'm going to have one of those y's divide out with that one. So really it looks like we're left with is negative y over x. That's much simpler, and it's going to be much easier to go with the derivative of this than it would be if we hadn't simplified this. So now we have to find the second derivative, which means we're going to take the derivative of that. Okay, so now the second derivative. Don't want to write that. Write it like this. All right, the derivative of dy over dx is the second derivative. Again, that's the notation. The derivative of the right side is going to be a quotient rule. You can technically put the negative sign wherever you want to. You can put it on the top, you can put it on the bottom, but you're going to need to include it somewhere, or you can just leave it off to the left-hand side. It doesn't really make any difference. Personally, I think it's going to be easier if I just leave it off to the left, and then I do the quotient rule of just y over x. So the derivative of the top, derivative of y, is dy dx times the bottom, x, minus the derivative of the bottom, which is 1, times the top, which is y, all over the denominator squared. Okay? So there's only one issue with this. The biggest issue is this one still has a dy dx in it. We can't leave dy dx there. But what we can do is, since we already know what dy dx is, because we found that, is we can replace dy dx with dy dx's derivative, or the actual derivative, which was negative y over x. So what we're going to get is negative y over x times x minus y over x squared. That parentheses didn't go long enough there. And then we can just multiply things through. X times the negative y over x here is going to get rid of that. So I'm going to get negative of negative y minus y over x squared, which is the same thing as the negative of negative 2y over x squared. And the negative is going to cancel itself out, leaving us with 2y over x squared. That is the second derivative implicitly. All right, a lot of information there. Definitely do your best to keep track of the implicit differentiation, because now we're going to be throwing that together with all the other rules and everything, and I know it gets to be a little bit overwhelming, but that's where we are. That should be plenty enough to get you started.